Hello and welcome. I'm Oliver, and today I would like to present you joint work with Benox on how to detect traffic ingress points at ISPs. For ISPs, this is a relevant problem for a number of reasons, and the first one being network performance debugging. So let's consider the following example. We have an ISP that provides internet access to both ADSL and fiber to the home users in one city. And at some point, the fiber to the home users experience a degradation in network performance for when accessing one particular website, whereas the DSL users are not. So ingress point detection was a tool by the ISP to debug this performance problem. And here the reason was that the concerned website was served by the CDN, and the CDN was serving the ADSL users from a nearby data center. However, the fiber to the home users were served by the CDN by a data center far away in a different country. And obviously what we're observing here is a problem of incorrect CDN mapping of fiber to the home prefixes. And ingress point detection was the tool that enables the ISP to detect such kind of performance problems. Another use case for ingress point detection is to implement better ingress traffic engineering schemes. So one use case might be joint CDN ISP traffic steering. That's a scenario where both the ISP and the CDN collaborate to find a jointly optimal ingress point for receiving traffic. And that, of course, requires the ISP to first know where the traffic actually enters the ISP's network, which cannot be a simple task since traffic can enter the ISP's network from any AS, not necessarily directly from the CDN. And here, ingress point detection is a tool that enables such a use case and can be used to implement it. Now, if we want to implement it, we are faced with a number of design challenges. And the first one simply being scale. Because in order to implement ingress point detection, we need to now monitor traffic at all the border routers. And in the case of our observed ISP, that means hundreds of border routers. The second question is the one of some granularity. So at what granularity are we observing and tracking this traffic? And here this problem is simply being that tracking ingress points on the basis of a single individual IP addresses does not scale. So we need to aggregate IP addresses into ranges that share the same ingress point. Now the question is, what granularity do we use? And here the answer is we want to have dynamic granularities that adapt to the traffic dynamics that we observe in the actual traffic, mostly from CDN networks. So a first question might be, okay, can't we use BGP for implementing ingress point detection because the data is easy to obtain? And the answer is no, BGP is not an option here. And the reason is actually illustrated here on the slide. So let's assume that the ISP announces its address space on all the egress links that we've shown here. And simply because the ISP is making such an announcement does not mean that also subsequently traffic follows on that link. And the very same is true for the announcements that we receive from the CDN. So just because we receive an announcement does not mean that also traffic follows on that link where we saw the announcement. A second challenge is that we observed in the paper that ingress points actually change often. So in our case, 60% of the ingress points are only stable for less than an hour, and only 10% of them stay on the same link for more than 6 hours. So that makes it necessary to run the algorithm regularly, let's say every minute. We also found that in most of the cases, there's only a single ingress point for a given IP or prefix at a time, even though we are observing multiple paths in BGP. In the case that we observe multiple paths, multiple ingress points, in many cases, there is a single ingress point that is dominant. So here we saw that for 80% of the prefixes, 80% of the traffic actually enters over a single ingress point. So we want the algorithm to be further able to detect this dominant ingress point that we are observing here. Now, with that, we arrive at the summary of our design challenges. So the ingress point detection algorithm is a scheme that performs a traffic-based partitioning of the IP address space. So obviously, we can't use BGP for that. We solely focus on net flow from all the border routers, and we want the algorithm to scale to thousands of routers to run continuous monitoring. With that, we arrive at a system design that is comprised of two stages. In the first stage, we're simply concerned with handling the massive influx of net flow from more than 3,000 routers in our case. And here the goal is to only collect the data and inject the incoming data into a data structure. This is something that can nicely be parallelized over many CPU cores. In the second stage, we're then concerned with the actual classification of the ranges and finding the dominant ingress point. In order to prevent race conditions, we only implement this let this run on a single CPU core. So let's demonstrate the algorithm by a simple example. So remember that what we're doing is performing a traffic-based partitioning of the IP address space. And you see the entire IP address space in the case of IPv4 as a rectangle here on the slide. So starting at quad 0 on the left-hand side and ending at quad 255 on the right-hand side. To store the data in our implementation, we use a binary trie as a data structure, actually two, one for IPv4, one for IPv6. In this example, what we're showing on the left-hand side is the current CIDR mask that we're looking at. And on the right-hand side of the slide, we are showing the parameterization that we're using. And here we see our first parameter, which is the maximum CIDR mask at which we stop the classification. Here in this example, this is set to /3. To ensure that we only make a classification once we have sufficient traffic received, we require a minimum amount of samples to be received in order to make a classification. In this case, this is 11 for the whole /0 range. Now, if we then later on split the ranges and look at higher CIDR masks, so smaller prefixes, we obviously also only require smaller amount of samples. Now, at time t0, traffic enters the ISP's network as we see here. As we know and as we have seen before in stage 1, we're just concerned with actually handling, parsing the incoming net flow and adding it to a data structure as we see in this rectangle here. In the second stage of the algorithm that is regularly executed at predefined configurable time intervals, here in our case 60 seconds, we then check first if we have sufficient amount of samples received, and then if we can find a dominant ingress point. In our case here, we have now received enough samples, but we see a wild mix of colors here. So obviously there is no dominant ingress point. So that means we further split the prefix into 2/1s as we see here on the slide. What now happens subsequently is, of course, the ISP is continuously receiving traffic that we enter to our ranges here, just as we have seen that before. Now again, we can check if we have enough samples received, which is not the case for the prefix on the right-hand side, but it is the case for the one on the left-hand side. Yet we still see a wild mix of colors, so we don't find a dominant ingress point. That means we further split the prefixes. And again, the ISP is still continuously receiving traffic that we enter into the ranges. And now we can again check if we have enough samples. Yes, we do. And do we have a dominant ingress point? Yes, we also do for the left-hand one. Here, all the traffic enters via the purple ingress point, so we can mark this one as a prevalent ingress point. However, we can't yet classify the prefix on the right-hand side. That means we will now continue splitting it. Now, since everyone knows that there's a huge amount of a certain amount of wild traffic, strange traffic, attack traffic in the internet, we want the system to be robust against that. So we add a quality parameter Q, which we set to 95%. That means we classify a prevalent ingress even though up to 5% of the traffic enters via any other link. So again, now at T3, we perform this splitting, and now at this time only one additional sample here arrives at the ISP, and then no further traffic is received from this single IP address. So what will happen now is that this sample at some point expires. The expiration time is configured by a parameter that we set here to 120 seconds. After this is done, we can again check if we have enough samples. Yes, we do. Do we have a prevalent ingress point? Yes, we also do for the red hand, however, not for the prefix that is on the left-hand side here. However, since we already arrived at our maximum configured CIDR range of /3, we're no longer or no further splitting this range here, and we simply stop. Please note that for simplicity of the illustration, we have now omitted various aspects, so as how we aggregate IPD prefixes again. Please refer to the paper for all the complete implementation details of our system. Now, as we have seen, we can control the system with a number of parameters. And in order to find the optimal parameter set, we have run a parameter study with more than 300 combinations of parameters to identify the optimal parameterization. And the result that we arrive is that these parameterizations do not change the accuracy, but instead they only impact the runtime and the resource consumption. And with this optimal parameter set, we let the IPD algorithm run in production at the tier R1 ISP for 6 years at a single commodity server. And this single server is enough to handle the net flow traffic that we receive from more than 3,000 routers, and which compromises about 4 million flow records that are received and processed by the system per second on average. So with that, I would like to give you a sneak peek into the evaluation of our algorithm. So we have validated the IPD detection accuracy by comparing the detected ingress points with the actual data from 25 hours of net flow traffic traces from the ISP. And you see the obtained accuracy here on the y-axis of the plot. And the gray shading in the figure shows the maximum normalized traffic volume, which follows a daily pattern as expected in the internet. So what we can observe here is that the ingress point detection is able to detect the correct ingress link for 91% of the flows on average. That's already a pretty good score. But remember that our design focus was to focus on high volume traffic prefixes, so the ones that are the most relevant for performance debugging and ingress traffic engineering. So we therefore have further identified the top 5 and top 20 inbound ASs by traffic. And here the ingress point detection performs even better, with 98% of the prefixes from the top 5 ASs were classified to the correct ingress link on average. However, there are a number of inaccuracies that we report in detail in the paper. And in a nutshell, these are due to traffic shifts, operational changes, and kind of expected changes in the network. In summary, we can say that the ingress point detection works well enough in practice for the ISP to build services on top of it. Now, a second interesting perspective on the ingress point detection is that it enables us to run the first measurement study on path asymmetry at the tier 1 ISP. So here we compared the ingress routers derived from the ingress point detection with egress routers that we obtained from BGP dumps for each prefix, and we show the symmetry ratio on the y-axis. Now, what we are observing here is that yes, there is path asymmetry in the internet. However, the amount of symmetric prefixes or the amount of asymmetric paths kind of depends by the network that we are looking at. So we are observing here the highest symmetry ratio by tier 1 ISPs. And if we now look at all the traffic and or just the top 20 ASs, we observe an asymmetry ratio of 30 to 40% asymmetric paths respectively. That also means that paths are asymmetric, so we can't use BGP for ingress point detection. Another use case, and that was actually a design requirement of the ingress point detection, was that we want the IPD to optimally adapt to ingress traffic dynamics that we observe. So what we're now doing in this evaluation is we compare the distribution of CIDR mask sizes that we observe in BGP, which are the gray bars, to the ones that we observe by the ingress point detection, which are the other bars. And here we see notable differences. So in BGP, 54% of the prefixes are /24s, whereas in the ingress point detection, only 15% are /24. More notably is that in the ingress point detection, 57% of the prefixes are more specific than /24. And this is relevant and interesting. Why? Simply because these prefixes are typically not announced in BGP, but they are the ones that are the most relevant for CDN traffic engineering. And here we see that the ingress point detection actually performs well and adheres to its design requirements. So in order to summarize the operational experience that the ISP has collected over the deployment period, the ingress point detection has been a valuable tool for network troubleshooting. It also enabled the ISP to implement additional services such as CDN ISP collaboration for traffic engineering. But more importantly, the main value of the ingress point detection is that it enables the ISP to talk to interconnected ASs about problems that it occurs. Of course, there are a few things that we omit, and one of them is router level load balancing, because that requires us to also attract the destination IPs in addition to the source IPs, which results in a quadratic additional complexity. And since we only observe a negligible amount of router level load balancing in the case of the observed ISP, we decided to omit this. If you would like to experiment with ingress point detection yourself, we have an open source implementation that we make available in the mini internet environment with a prototypic ISP scenario with CDNs that you can download and run at your server. With that, I'm at the end of my talk and would like to thank you for your attention.